Sure. Wherever you can find it. But I want you to have this figured out. Before we start today's lesson, I want to rehash some things that we know about exponential graphs. Okay? You got to be able to tell the limits as x goes to negative infinity. What does this look like? You got to be able to say that stuff. And that would be so helpful if you could remember it in the future. Right? Because we've been over it, but, you know, life happens. So I'm talking about, you have graph paper? Yeah, wow. Whoa. All right, so exponential graph review. Guys, we're talking about functions that are in the form of f of x equals, what's the parent function or the general form of an exponential graph?
AB to the x.
See, a times b to, this is why we keep Joseph. He knows things. A times b to the x. Okay? So given a couple of situations, we know that if b is greater than, not greater than 0, I need to fix that. If b is greater than 1, we see exponential growth. If b is greater than 1, we see growth. That means that this function is going to get big, fast. It's increasing. Okay? Now, we have two cases for growth. One situation for growth would be if a is greater than 0. Notice that I drew this picture above the x-axis. Above the x-axis. Okay? So a couple of features that this equation has, besides being greater than 1, b being greater than 1, a is greater than 0. So it's positive. You could say this function is increasing. I don't have room to say increasing, so I'm going to say inc. You need to know that means increasing. What else? Talk to me about its concavity.
It's concave up.
It's concave up, like a cup. Okay? And now let's look at the limits. This would be as the limit as x approaches positive infinity, what does f of x do? F of x goes also to positive infinity. And on this tail, the limit as x goes to negative infinity, what does f of x do? Goes to 0. This is classic of exponential functions. One tail is going to go to 0. The other tail is either going to go to positive or negative infinity. Okay? Now, let's say that b stays greater than 1. We stay with something like 3/2 or 4. Okay? But that initial value, that a value, instead of being greater than 0, let's say that initial value happens to be less than 0. What's that going to do to this function? It's going to flip it. Same as it always does to our functions. It's going to reflect it over the x-axis. If now a is negative, then we're reflected. So instead of being an increasing function, now this is a decreasing function, and it is concave down, like a frown.
Big sad.
Okay, talk to me about the limit of this tail. What's it doing? The limit as x approaches positive infinity of f of x is negative infinity. Now it's trending downward. It's decreasing. Talk to me about this tail. The limit as x approaches negative infinity is going to 0. Yeah? Okay. Now, let's get on the other side over here. Now we're talking about b being a number between 0 and 1. What kinds of numbers are between 0 and 1? Give me some.
0.3.
Fractions or?
Decimals.
Fractions or decimals. So in this case, we're dealing with exponential decay. Decay, meaning that something has been shrinking. It may have started out pretty big, and as we get closer and closer and closer to positive infinity, I'm thinking like exponential decay is maybe a half-life of carbon or something like that. Or maybe it's that humongous cupcake that I brought to class, and then I split it and split it and split it and split it. Right? You with me? Okay. Yeah, one of these days. Notice that in this case, A is greater than 0. So my picture happens to be above the x-axis. Yeah? Okay. So on this particular function, we could say it is decreasing for all values of x. There's no inflection point. There's no extrema. No sense in time where it's going to change from decreasing back to increasing. Once an exponential function is decreasing, it is always decreasing. Okay? There are also no inflection points. So there's not an extreme that would make it change max to min. There's not an inflection point that would make it change concavity. Once you know that this thing is concave up, it's always concave up. Cool? Talk to me about the limits. This is going to be the limit as x approaches negative infinity of f of x, positive infinity, to infinity and beyond. And on this end, the limit as x goes to positive infinity of f of x is
0.
okay. Now, let's say that b stays between, right? Stays between 0 and 1. We're still talking about exponential decay. But let's let that initial value be negative. So it flips it. It's just a reflection over the x-axis. You with me? So this still represents decay. But now it's negative decay. So what's this function doing? It's increasing on all values of x. And it is now concave down like a frown. Right? And so if you threw your limit behavior in here, or your end behavior, limit as x goes to negative infinity of f of x now is going to be negative infinity. And the limit as x goes to positive infinity of f of x is 0. You will never have no cookie. But it goes to 0. Right? These are the 4 cases. This is it. But you better be able to come up with these cold. And the rules for them are if a is greater than 0, we're above the x-axis. If a is less than 0, we're below the x-axis. You got to know when is it growth and when is it decay. And then look at your a value to see where am I located. Yeah? Mm-hmm. Is this feeling better? Look at me. This is the only time we hit this. We might, because yesterday I had nightmares. So we better be able to come up with this cold. Yeah? Okay, so going into today's lesson, logarithmic functions. Let's take everything we just learned and not throw it out the window, but do it backwards. We're going to invert it.
What? You just like seeds.
Here we go. So because logarithmic functions and exponential functions are inverse functions, the characteristics of their graphs will have inverse relationships. Okay, so not for nothing, we just went through exponential stuff so that we can look at logarithmic stuff. A logarithmic function has the general form f of x equals a times log base b of x, where b is greater than 0. A and b are constants with a not 0 and b not 1. Okay? The domain, because these functions are inversely related, look at the range of our exponential functions. Look at, just specifically, let's zero in on this guy right here. What's the range? All real numbers greater than 0. So the range here would go from 0 to infinity. Yeah? Check out the domain on this one. 0 to infinity. You see that? The range on the other one, or the domain would have been all real numbers. So the range here is all real numbers. They're exactly inversely related. A logarithmic function has a greater than 0 and b greater than 1. Check it out. if a is greater than 0, where is it located? Not necessarily above the x-axis. Instead, we're looking at it being to the right of the y-axis. Yeah? Okay. That translation, what we're saying is instead of being all above the x-axis, now it's to the right of the y-axis. Because I'm using a marker. Quit crying. Okay, if I'm talking about exponential, if I flip it, that's what I'm saying. If I flip it, notice that now a is less than 0.
Why is b always greater?
Because this is, there's no way to have a base that's negative.
Okay.
Not going to have a base that's negative. Okay? You can't log a negative number. It's not going to happen. Okay. Yeah.
She said it doesn't.
All right, so here are some things that we want to look at. Logarithmic functions are always either increasing or always decreasing. They're just like exponential functions. There are no extrema that are going to make that change. And then they're always concave up or they're always concave down. There are no points of inflection along the way that will change that either. End behavior is going to be very similar. You're either going to have an end going to positive or negative infinity, or you're going to have an end going to, actually, these ends don't ever go to 0. It says, since logarithmic functions have a restricted domain, they are vertically asymptotic at x equals 0. As a result, the left end behavior will occur as x goes to 0. So instead of having one of your tails go to 0, you're going to have the limit go to 0. Okay? So instead of saying the limit as x approaches infinity, f of x goes to 0. It's backwards. It's the limit as x goes to 0. See?
F of x goes to
Infinity. Right. So instead of taking x to infinity and f to 0, we're taking x to 0 and f to infinity. Okay? There's a reason we went through all of that just now. All right, so let's work example 1. It says write limit statements for the end behavior. Okay? So looking at number 1, or part A, the limit as x goes to 0. What's that little plus sign up there mean? From the right. Okay, so it's not positive 0. It's from the right side. What's f of x doing? Where's it going? Negative infinity. F of x goes to negative infinity. And on the right, how would we write this limit statement? Limit as x goes to positive infinity. Do I have to say from the left? No, because there's only one way I'm going to get to positive infinity, and that's from the left. Right? Of f of x is positive infinity. This thing's growing. It's not growing as quickly as an exponential function, but it's still going to positive infinity.
Is x approaching 0 still?
No, this is x approaching positive infinity.
On the bottom?
Okay. Going on to B, on the left side, which way is x going? As x goes to what?
0.
0. That x value is going to 0. From the right, f of x goes to, now it's going up. So f of x goes to positive infinity. So I'm saying in this case, I'm going to 0 in x, so f of x is going up. Does that feel better? Which way am I going with this tail? To the right. The limit as x goes to what? Positive infinity. Of f of x goes to negative infinity. Because it's going down.
2 log would be on top. And then 3 is greater than its growth.
Okay.
So it would be...
So part C, we're kind of looking at the legend that we had up on the previous page or right above your page. If A is positive, If a is positive, so that's the number in front of the log. If a is positive, then it looks like this. Lies. I drew an exponential. Gosh, I get so twisted with these. If a is positive, then it looks like this.
Wait. I got it. Wait, so if x is going to 0, then it's positive. Then.
So the left side would be the limit as x goes to 0 from the right of f of x is what? Negative infinity. Good. I know. And on the right, the limit as x goes to positive infinity of f of x is positive infinity. So your tails on logarithms are going to be infinities. One of your limits is going to be x to 0. The other one will be x to infinity.
Wait, so the reason why that one's concave up is because it's decaying.
So if it's left,
H of x. And then this one is...
Concave up. So it's not, you're not looking at it as growth or decay. It's a logarithm. Uh-huh.
is the left like x always going to be x approaching 0 from the right?
Mm-hmm.
Always. I don't know if that was a yes or not. So not?
Words like always scare me.
For now. For now. I guess it.
On these three. All right, let's go on to example 2. Example 2, it says for each of the following determine if the logarithm function is increasing, decreasing, and concave up, down. Did y'all get straightened out over there? You think so? Okay. So look at A. It is concave what? Up, like a cup.
And it's decreasing.
And it is decreasing. How do you know, Truett?
Because it's going down.
Because it's going down. Because my tangent lines here would all be what?
Down.
Negative. My tangent lines would all be negative. Down. Letter B. Concave down, like a frown, but it is increasing. How do I know it's increasing?
It's going up.
Because my tangent lines are positive.
This one's con.
I like Justin's.
Okay, let's talk about this one. Okay, this has a negative A. So what's supposed to happen, if A is positive, the general form looks like this. Okay, but in this case,
It's a log, so it's flipped.
it's flipped because your A is negative. So they took what you should see. Parent function for logarithm looks like this. Okay, that is generally what happens. When that A is negative, it's reflected over the x-axis. So what we're dealing with on this particular picture, because that A is negative, is this. Except know that A is negative. So it is concave what? Up like a cup, and it is... Okay. Okay, so parent function, you got to know. And the way that I keep that straight, y'all listen. I know this. I know that an exponential function, growth technically is usually what we see. We see y equals b to the x. That's the most general form, right? A logarithm is going to be the exact inverse of that, which is going to look like this. So this, for me, is the log parent function. Y'all with me? So I'm going to start with this blue one in my brain. Now, they flipped it. So what does that look like? This. Yeah? Never say never. Not in this lesson. All right, number 3, example 3. It says selected values of several logarithmic functions are shown in the tables below. Oh, these are puzzles. How many of y'all like Sudoku? Sudoku. These are puzzles. Y'all are going to really love this if you'll let it be a puzzle. Except I don't know how to explain it so well, except that's what we're doing. All right, so look at the example. Number 3, look at the table. We are. So we've got 1 to 2. Check out your x values. They're increasing on equal width intervals. We kind of hammered that yesterday. You can tell that these y values are increasing by the same rate every time. Okay? Your x values are supposed to be doing something multiplicatively. So what does that indicate that k might be? 4. Okay. K is 4. Good.
That makes sense.
Good. Moving on. G of x on the second piece is increasing by 5 every time. Adding 5.
It's 2.
What's x doing? It's increasing by a multiple of 3. So if I'm going to go backwards, I'm going to divide 6 by 3, and now k is 2. Good.
Oh, wait, hold on.
Okay, here we go. Look at h of x.
No.
It's 11.
It's 11.
Is it actually?
It's 11.
Oh, I completely guessed.
Oh, man, I was hoping you were going to get to explain, because I don't want to.
That's what plus
It's 11.
plus 2, so I was going to do plus 3 and it's 10, but then
Oh, because it's 4, and then it would go to 8, so it would be 19.
What?
What it's adding by multiplies by 2 each time.
Girl, hold on.
That's how it works.
What?
No, because look, it goes 4 to 5, so it's 1, and then it goes 5 to 7, so it's 2, so it's multiplying times 2. Then 2 times 2 would be 4, 4 times 2 would be 8, which would give you 19. Yeah.
It's 11. Okay.
So you're going from 4 to 5, you're adding 1.
Yeah.
Okay.
Then 5 to 7, you're adding 2, which is 1 times 2. Now 2 times 2 again would be 4, which would make k 11. Now to make that add up, 4 times 2 would be 8, and 11 plus 8 is 19.
That makes sense.
So at the end of the day, k is 11. Okay, so let's back up. Okay.
I might need to see. Can you write that out, Julia?
Yeah, no, I'm writing it out.
Question.
Okay. So
This is
4 to 5 is 1. 5 to 7, the difference is 2.
question mark.
4.
We need a 4 to be the difference
The
here.
rate of change is double.
So that the rate of change between k and 19 can be 8. Really? Okay, good. I'm glad.
Yeah, it does.
Oh, yeah, now you can't even just look at the numbers. I have to look at the rate of change.
I know.
Oh,
So to get from 4 to 5, we had 1. And then from 5 to 7, the growth rate is 2. So the rate of change here is doubling every time. And in order for that to happen, we need to hit 4 more than 7, and then 8 more than that should be 19. Okay. You said it was 11, and I really was impressed, but okay. All right, so now we're looking at this last example. Something's happening in E. We're going from E to the -2 to E to K to E to the 7th to E to the 10th. So what's happening on that power every time? And in this case, the Y values seem to be adding 7. That's kind of boring. So what's happening in the exponent position over here? I'm starting with e to the -2, and then I have e. Then I have k, e to the 7th, and then e to the 10th. It's not e cubed. No. E to the 4th. The exponents are going up by a third power every time.
I don't like it.
So k in this case is going to be e to the fourth. Right? I told you they're puzzles. Are you lost? Uh-huh. So we go from e to the -2 to e. That would be e to the first. So how am I getting from -2 to the first power? I'm adding 3 to that power.
Yeah, I mean, you could just essentially we're thinking of it as e to the 0, which
Okay.
is not.
It's e to the 1.
I did too, I did 0.
Yeah. Yeah.
I did the same thing. It's all the-
Cool. Are we good here?
Yeah, sure. Great.
Yeah? Okay. All right, now we're moving on to example 4, and this is where things get really, really necessary for you to imagine that parent function where a is greater than 0, right? And we're looking at it like this. This is the parent function. You want to keep that visual in mind. So what's going to be the domain of f of x if that's the case? The domain is going to go from 0 to infinity. Agreed. Is it ever going to touch 0?
No.
So on that side, we're going to have round parentheses. And the range? Right. Negative infinity to positive infinity. Good. Okay. So now on part B, they flipped it. So instead of looking like this, for part B, you're going to see this. Flip it. Come on, Arminta. Like this.
It doesn't go to 0, it goes to +3.
Okay, so the range would be, or the domain would be 0 to positive infinity, except they scooted it. Look at that, x minus 3 business. Which way did they translate it? Insiders do what? Lie. So that thing went right 3. Good. So now instead of going 0 to infinity, it's going to go 3 to infinity. Very good. We know that that went right 3. Nice. Very good. Excellent. Everyone gets a cupcake. I still haven't brought y'all cupcakes. What's the range?
Negative infinity, positive infinity.
Good. So range hasn't changed. How could they change the range?
They can't.
You can't. It's always negative infinity to positive infinity. They could shift it up, but that range is not going to change. So it wouldn't change the range. Yeah. All right, now let's look at part C.
Oh, it's a positive.
Positive 8. Positive 8. So now we're looking back at the parent function idea where we're doing like this. But instead of going from 0 to infinity, look, we've got a 2x plus 3. Now, you don't want to look at horizontal shifts without factoring out the 2. Okay? So we really want to look inside this parentheses as 2 times x plus 3 halves. Because I can't look at a shift without seeing a naked x. So I pulled the 2 out. Are y'all understand what I'm saying? You can't see the 2x and then look at a shift and understand anything. It has to be a naked x. So you're going to factor out the 2, which means now I'm looking at x plus 3 halves. Which means it went which way? Left. How many?
3 halves.
Left 3 halves. So now what's the domain? Negative 3 halves to what? Positive infinity. And it's not going to touch. It's asymptotic at negative 3 halves. Good move. And the range?
Negative infinity, positive.
Yay. Now we can call it a day, says Megan. Any questions on that one, y'all?
There's no homework or anything like that, right?
No, yeah, no.
It's attached.
I didn't see it, so it doesn't.